And we're going to move on to something called multidimensional scaling. And it sounds very scary, multidimensional scaling. But if you understand PCA, or at least the main ideas behind PCA, multidimensional scaling is going to be a snap, and we're going to plow through this really quickly. Okay, so before I get started, I just want to let you know that there's actually two types of multidimensional scaling. There's something called classical or metric multidimensional scaling, and then there's something called non-metric multidimensional scaling. Today we're going to be talking about classical or metric multidimensional scaling. Classical multidimensional scaling is also called principal coordinate analysis, PCOA, which sounds cool, but I think multidimensional scaling sounds cooler. It just sounds so fancy and sophisticated. Anyways, so let's get back to our normal cells. And like I said, if you're not a biologist, these could be people or cars or cities. And like we just saw, even though they look the same, we suspect there are differences. And these could be one type of cell or person or car or city. These could be another type of cell. And these might be a third type of cell. Unfortunately, we can't observe the differences from the outside. So we sequence the messenger RNA in each cell to identify which genes are active. And this tells us what each cell is doing. And we could also measure other things if we were looking at other things. Okay, so here's our data, just like we just had a few minutes ago. Each column shows how much each gene is transcribed in each cell. Boop, 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 boop. And when we did PCA, we converted the correlations or lack thereof among the samples into a two-dimensional plot, or we did it with singular value decomposition, and we projected it into some high dimensional space, and we found that best fitting line, and we called that PC1, and we found the second best fitting line that was perpendicular to PC1. We called that PC2. Okay. So highly correlated samples form clusters. Okay. So multidimensional scaling, MDS, and principal coordinate analysis, PCOA, are very similar to PCA, except that instead of converting correlations into a 2D graph, they convert distances among samples into a 2D graph. And I'll show you what I mean by distances among samples in just a second. So in order to do MDS or PCOA, we have to calculate the distance between cell 1 and cell 2, and the distance between cell 1 and cell 3, and the distance between cell 1 and cell 4. And then we calculate the distance between cell 2 and cell 3, and the distances between cell 2 and cell 4, etc., etc., etc. Okay, for now, let's imagine we only need to calculate the distance between cell 1 and cell 2. One common way to calculate distances between two things is to calculate the Euclidean distance. If we just had two genes, we could draw a line that represented the difference between the values for gene 1. So in cell 1, we've got 3, and in cell 2, we've got 0.25 as the values for gene 1. And we can do that math, do that subtraction, and that equals 2.75. And we can draw a line that's 2.75 units long. Then we could draw a line that represents the difference between the values for gene 2. So in cell 1, the value for gene 2 is 2.9, and in cell 2, the value for gene 2 is 0.8, and we do the math, and we get 2.1, and so we can draw a line that is 2.1 units long. Then the Euclidean distance would be the hypotenuse, and that's the Pythagorean theorem. So b squared plus c squared equals the hypotenuse. When there are more genes, we just add the square of more differences between genes. The difference for gene 1, the difference for gene 2, and this is actually a copy and paste error. That's actually supposed to be the difference for gene 3, but it looks a little messy. It should be 2.2 minus 1. Anyways, et cetera, et cetera, et cetera. We just do that for each gene in our list of genes that we have. And ultimately, we calculate a distance. And once we've calculated the distance between every pair of cells, MDS and PCOA would reduce them, all those distances, to a two-dimensional graph. The bad news is that if we use the Euclidean distance, the graph would be identical to PCA. So so we've done PCA 3 different ways. We did it with singular value decomposition. We looked at it with using covariances and correlations. And now we've done it again with something called multidimensional scaling, using the Euclidean distance as our way of measuring distance. In other words, clustering based on minimizing the linear distances is the same as maximizing the linear correlations, or fitting that line so that we maximize those distances between the projected points and the origin. The good news is that there are tons of other ways to measure distance. For example, another way to measure distances between cells is to calculate the average of the absolute value of the log-fold changes among genes. And unless you're a geneticist and working with high-throughput data, may sound completely bizarre, but if you work with genetics data, people are looking at log-fold changes all the time. We'll have we want to see sort of like what's the difference in how this gene behaves in different situations, and we'll say, oh, this gene had a log fold change of 2 or something like that. And that's how we often will kind of talk about changes. So for the example, the log fold change for gene 1 versus, and we're just looking at cell 1 and cell 2. We're not looking at the other cells right now. The log fold change is just the value for gene 1 divided by the value for the value for cell 1, which is 3, divided by the value for cell 2, which is 0.25, and then we just take out the log of that ratio, and that's the log fold change. So the log fold change for gene 2 is the log of the ratio of cell 1 to cell 2. Bam, bam, bam. We just do a lot of those. And then we do that for everything. Okay, so now we've calculated all of our log fold changes, and then we take the absolute value. So some of those logs are negative, and some are positive, and we're just making them all positive. So they're all greater than 0. Lastly, we take the average of the numbers, and that's the average of the absolute value of the log fold changes among genes. And remember, this is just between cell 1 and cell 2. And so this is the average that we end up with of these values. The average of these values is what we're going to call the distance between these two things. Again, one of the reasons why we're taking the absolute values, we don't want this negative value to cancel out the positive values. We want to have every distance additive and just make it, further and further. Anyways, that's what I just said. Bam. Okay. Ultimately, we get graphs that look different. So on the left-hand side, we've got the MDS plot using a Euclidean distance, and that's the same as our principal component analysis. On the right-hand side, we've got the MDS plot using log fold change. So we had a different distant metrics, and we end up with a different graph. If any of you guys are familiar with there's this thing in genetics called differential gene expression. There's a program called DESeq2 that people use to decide if genes are different from each other. And by default, it gives you, when you put in all of your data, it gives you this graph on the right. It gives you an MDS plot using the log fold change as the distance metric. Okay, as a biologist, we might choose to use log fold change to calculate distance because they are frequently interested in the log fold changes among genes. That's just something biologists are interested in. However, if you're not a biologist or a geneticist, there are lots of other distances to choose from. So for example, there's something called the Manhattan distance. And that's basically, if you just assume you're like in a city with city blocks and you can't go diagonal, you have to kind of go up and over. The Manhattan distance is a sort of up and over distance. And so if you're routing Uber, taxi cabs or something like that, you might want to use the Manhattan distance to get a better sense of how what cars are close to each other, because they could be on the same block, but if there's that diagonal distance between them, that might look short than it really is, because the cab or the Uber guy has to go all the way around the whole block. And so there's different distances for different sort of areas of expertise. And one thing that's nice about MDS is it allows you to use those distances in a PCA-like way. And to be honest, there's no rule for how to select the best distance, and that's kind of the part of the art of data science. Okay, so in summary, PCA creates plots based on correlations among samples, or fitting those best lines. MDS and principal coordinate analysis, I'm stumbling all over my words, create plots based on distances among samples. And so PCA correlations, then we do some fancy math, eigen decomposition, or we do singular value decomposition, and out of that becomes coordinates for a graph, and it gives us the percent of variation each axis accounts for. And it also gives us loading scores, so we can determine which variables have the largest effect. MDS and principal coordinate analysis, the only difference is that we can select different distances. So if you understand PCA, just know that the only difference with multidimensional scaling is that we've just, instead of using the Euclidean distance, we're using the Manhattan distance, or we're using this log-fold change distance, or whatever kind of arbitrary distance we want to use. But the math, the fancy math, is the same, and the output is also the same. We get coordinates for a graph, we get percent of variation each axis accounts for, and that gives us our scree plot, so we can say, hey, it makes sense to reduce this down to 2 dimensions, or maybe it doesn't. And it also gives us loading scores, so we can determine which variables have the largest effect. So bam. Okay, so now we're going to do another pause. I'm going to stop